Do you know people walking on floors and cars moving on bridges cause some kind of loading? But the real question is that how do we design for this loading and how does this loading look like? What does it mean by 5 kilonewton per meter square? What does it mean by 100 pounds per square feet? In this lecture, you will learn about floor loadings and how floor loading is transferred all the way from roof to the foundations. Hey friends, if you're new here, I am Dr. Jawed Qureshi, a senior lecturer at a London university. On this channel, we explore technical and human skills to help us lead more productive, happy, and examine life. In this lecture, I will talk about how floor loads are transferred in buildings. This is the outline of today's lecture. First, permanent or dead loads, which are denoted by G. Second, variable or live loads, which are denoted by Q. Member loads or internal forces, which develop in structures. Load path for simple structures. And finally, how to work out loading in simple structure. First, loads or actions. We have to assess loads really properly and precisely to be able to design any civil or mechanical engineering system. The loads can be direct loads or direct actions which are applied to structure. If a point load is applied to a structure, that is directly applied to a structure. For example, if this is a simply supported beam, if I am applying a point load, by point load, I mean that if a beam is resting on other beam, that will cause a point load. The loads can be indirect actions as well, which means that deformations caused by temperature changes in any structure, they are termed as indirect actions or indirect loads. We have to include all loads and all loading combinations, and we have to see load path as well to be able to analyze a structure and design a structure properly. Types of loading. We have external loads, and mainly here I will be considering loads due to gravity, and these are mainly vertical loads. This includes permanent loads or permanent actions, which are denoted by G. Variable actions or live loads are denoted by Q in Euro code. Different design codes will have different notations. Then we have internal loads or member loads. These are very important. When we are applying loads externally to the structure, the loads travel through the structure all the way to foundations. And during this travel time, they cause some internal loads. For example, bending moment is internal load. Axial loads, tension, compression, these are internal loads. And then we have reaction loads. So for example, if a person is walking on a floor, it will cause some kind of reaction on the floor. For example, my weight is 80 kg. If I'm walking somewhere, my two legs will transfer 40 kg each on floor. Then we have lateral loads as well. This includes wind loading, earthquake loading, or any other lateral loading. Lateral load normally pushes the building or a structural systems, and a complex phenomena, aerodynamics, is used to deal with these loads. But here I'll be mainly focusing on vertical or gravity loads. First, permanent or dead loads. These include self-weight of a structure, beams, columns, floor slabs, walls, roofing, windows, all will have self-weight. We have to ensure that the building at least, or any car or any other system, at least stand on its feet. This is done by working out its self-weight. Any permanent fixtures, permanent objects which are permanently attached to a building or a structure is termed as permanent loads. These include electrical fixtures, furniture, or plumbing. Self-weight of any structure is worked out by element size multiplied by its material density. So for example, if I have a concrete foundation, its self-weight is going to be, for concrete, it will be 24 kilonewton per meter cube. And if I multiply it with the area of the foundation, which can be 0.6 times 0.3, I will get something like 4 point something kilonewton per
meter of that foundation. If I'm working with steel, then its density will be 78 kilonewton per meter cube. If I'm working with timber, its density could be 4 kilonewton per meter cube. If I'm working with rubber, its density is going to be very less, like 0.5 kilonewton per meter cube. It really depends on the density. So denser the material is, it will have more self-weight. The masses are listed in Euro Code 1, which we use in Europe, and American standards as well. They have their own masses listed, or we can find it out in manufacturers' booklets as well. So for example, if you're using a composite beam with profile sheeting slab, in that case, you will find its self-weight in the manufacturer's guidelines. What is variable or imposed load? Variable means something that changes. So this load often changes its location and often changes its magnitude as well. And it is imposed when a structure is in use. So when we're using the structure, for example, if we're walking on the structure or cars are moving on a bridge, that will have imposed load. Imposed load varies in magnitude and location as well. If I'm walking on a bridge, a footbridge, I'm changing my location of feet. And if some other person is walking, its weight might be different, 50 kg or something. So the magnitude is going to change. Variable loads include weight of people. They include temporary objects such as machinery, equipment, or furniture, which is not permanently fixed. It includes traffic as well. So when traffic moves over a bridge, it changes its magnitude, it changes its location as well. Snow, it includes wind load as well, but here I'm just talking about the vertical imposed load. These are typical variable loads included in Euro Code 1, which we use in the UK and in Europe and in some other Commonwealth countries. In North America, they use pretty much similar loads as well. So for roof load, where sloping is less than 30 degrees, we have 0.6 kilonewton per meter square. Distributed load, residential floor load is 1.5 kilonewton per meter square, and school or classroom floor load, office floor loads are a little bit higher, which is 30 kilonewton per meter square. Retail spaces will have higher as well, 4 kilonewton per meter square. 3 kilonewton per meter square is roughly 60 pounds per square feet. 4 kilonewton per meter square is roughly 85 is 100 pound per square feet or PSF. The real question is that what is 1 kilonewton? It is very important to communicate these loads really properly. If we don't communicate the loading properly, then people will not understand. And you would observe on construction sites that people will not know what does it mean by 1 kilonewton. They want to relate with something. And here I will tell you what does it mean by 1 kilonewton. 1 kilonewton is roughly 1 kg is roughly equal to 9.8 newtons. I can say that 1 kg is equal to 10 newtons, and if I multiply both sides by 100, so 100 kg will be equal to 1000 newtons. I can say that 1000 newtons means 1 kilonewton. So 1 kilonewton is equal to 100 kg. What do you think what would be weight of adult African elephant? What do you think what would be the weight of 4 bags of cement? Clearly, 100 kg is 4 bags of cement, which means 1 kilonewton. African elephant is roughly, on average, 4,000 kgs or 40 kilonewtons. How much is 30 kilonewton per meter square floor load? Quite often, we don't visualize that how much load do we have on floors. And quite often, we over-design these structures. And here, this is really very interesting study by University of Cambridge. And what does it mean by 100 PSF load and demonstrating flow load? These are 2 reports which I have used to demonstrate that. This is the area considered. So here we have 498 centimeter in this direction, 125, we have 250, 300, and then 295 centimeter in this direction. So I will play this video. This is really very interesting. So you will see the changes in the pattern. 1.18, 1.4, 3.4, 5.6. This video demonstrates loading from 0.54 to 5.6 kilonewton per meter square, or 11 psf to 117 psf. Firstly, we have 0.54 kilonewton per meter square when there are 10 people sitting in the room, and it will look like this. Then we have 1.18 kilonewton per meter square, full meeting room with 23 people. And then we have 2.3. Now people can't fit in, so they have to remove the table. And now we have 29 people over 9 meter square area. Then we have 2.8 kilonewton per meter square, 29 people over 7.5 meter square area. People are getting cramped now. Then 3.1 kilonewton per meter square, 29 people over 6.75 meter square. 3.5 kilonewton per meter square, where 29 people are standing over 6 meters square of area. They are even more cramped. It looks like London Tube here. Then we have 4.6 kilonewton per meter square, where 29 people are standing over 4.5 meters square. Then we have 5.6 kilonewton per meter square, 29 people over 3.75 meters square. It means that now they have to raise their arms to fit in. On a typical busy day, this will be London Tube. When you are traveling to central London, you will have to stand like this. Variable load. Variable load includes that changes in magnitude and changes in direction, changes in location. Lateral or horizontal. This is mainly lateral or horizontal load. Due to thermal movements of airflow over Earth's surface, wind happens. This depends on environmental factors such as temperature or pressure gradient. This also depends on physical factors as well, such as local topography, location, and height of the structure. Wind is mainly a lateral load or horizontal load. But here I will not talk about wind loading. Eurocode 1, part 1.4 deals with the wind loading. Design or factored loads. In almost all design codes, we multiply loads with certain factors so that we are sure that the structure is safe enough, so that we are sure that our estimation, there could be mistakes in our estimation. So to account for those estimations, we factor the loads. In America, they call it as load and resistance factor design. In Europe, we call it as limit state design. So we have STR limit, where strength governs. And most of the structural elements, strength will govern. Design value of internal force or moment, it is denoted by ED, where ED is 1.35 GK plus 1.5 QK. GK is characteristic permanent load, QK is characteristic variable load. Note the difference between these factors. It is 1.35 for permanent and 1.5 for variable. The reason we have more factor for variable action is that variable actions are difficult to estimate. So there could be mistakes in estimates. That's the reason we have more factor in variable action. GK is permanent action, as I already mentioned. QK is characteristic variable action. So when we are designing the structure, we will always multiply these factors if we are checking its strength. But if we are checking its deflection, then the load has to be unfactored. Now, internal forces. What does it mean by internal forces? And there are three main internal forces. One is normal or axial load, which includes tension or compression. Second is moment. And third is shear force. Torsion is a kind of moment as well. Tensile load happens when we have tension or extension of the element, when we are stretching the element. If this is the member, if I'm stretching it, that will induce tension. And most of the time, you can observe it in cable stayed bridges, in trusses, you will have tension members. Compression means that if I'm trying to squash this column, if I'm trying to apply load from top and bottom, it will cause compression. It will cause shortening in the member. Columns are typical example of compression members. Bending, if this is a beam, if I'm applying loading in the middle, you will see that it is bending and it will look like this. So bending can happen in beams and it can happen in columns as well. That will have lateral torsional buckling. So this is a column vertical member. If I'm applying loading, it is buckling sideways. And shear is simply slicing two elements. This can be demonstrated here. Torsion is when you are applying moment along the longitudinal axis. So if this is the structure, if I'm trying to twist it here, that will include torsion. Now here it is member under combined loading. Torsion is being applied and compressive load is being applied as well. It is extremely important to understand load path. This is the example of Exchange House in London. In green, you will see this arch which is taking compression. And then you have these elements which are taking tension. And then you have bottom element which is taking tension as well. Now columns here all are supported on this compressive element. So this is how load is transferred. The second example, a very useful example, is Eiffel Tower, where wind load is being applied like this, and the force is, dead load is transferred through this bracing system, yellow arrows, and then again it is transferred here. At the bottom, you can see reaction, and here this arch is giving us compression, and finally it is transferred to the ground. And then this is Olympic Velodrome, not very far from where I work. Top elements, they are causing tension, and then these elements in green, they are causing compression, and finally we have reactions, horizontal, vertical, and moment. The examples that I'm going to solve today are taken from this book, Introduction to Structural Mechanics by Paul Smith. The first example is load on simple structure. Here, the dead load as imposed or load or variable load is given. So flat roof has got this much loading. Wall has got loading as well, floor and foundation. This is the section AA, and this is the plan of the building. I would assume that for foundation, they would have used concrete. For floors, they would have used timber. And for wall, it's brickwork. If you multiply the density of these elements, you will get these dead loads. So for example, for foundation, it would probably be concrete, so 24 kilonewton per meter cube times the area of the concrete, which is 0.6 times 0.4. You will roughly get this value. And for floors and walls, I would assume that walls are brick, so brick wall has density of probably 18 kilonewton per meter square. If you multiply it with the thickness of the wall, probably roughly you will get this value. Let us see how we can find out the loads transferred. Here the factors are not multiplied. So first we have flat roof, 0.75. Dead load is 0.75 kilonewton per meter square. So the load will be transferred from half of the roof to this foundation, and half will be transferred to this foundation. So the bay width is 5 meters, half is transferred, so that's why I will multiply it with 5/2. And again, same as the case, I will multiply imposed load with 5/2 to get the total load in kilonewton per meter run of the foundation. Then I have wall. Wall is 3.5 kilonewton per meter square. For wall, I will multiply always its height, because I want the load to come on these foundations, and I would like load in kilonewton per meter, which means that I would like it on the length of this strip foundation. And that means that I have to multiply all other dimensions. And here I'm assuming that thickness is already multiplied in 3.5 kilonewton per meter square. And then other dimension is the height of the wall and length of the wall. So I will not multiply with the length of the wall, because that's what I want. And then I will multiply it with the height of the wall. So height of the wall is 6, and we get 21 kilonewton per meter. Wall does not have any imposed load. And then I have floor load. I've used the same logic as I've used for flat roof. to multiply it with the half of the span. Foundation load is in kilonewton per meter already, because that's how we obtain foundation load. In that way, I will add up all the loadings and total load will be equal to 36.225 kilonewton per meter run on the foundation. This is unfactored load. So normally we'll multiply them with factors, 1.35 for permanent and 1.5 for imposed loading. Then I have another example here. I have a pitched roof and I have cavity wall and I have brick wall and I have floor 1 and floor 2. Each has got its own loading. So first we will start from pitched roof. So pitched roof is 12 meter in length. So half of the load will be transferred on foundation C and half of the load will be transferred on foundation A. Foundation B, on the other hand, is not taking any loading at all. Let us see. Again, this is the total load on pitched roof. We are adding up dead and live load, cavity wall and brick wall, and then we have floor loading. So simply add up the loading. The first is pitched roof. Total load on pitched roof is 1.9 kilonewton per meter square. We will multiply it with half of the span of pitched roof. Span was 12, so that's the reason we multiplied with half. And again here we will multiply 12 over half to get 11.4 kilonewton per meter on foundation A and foundation C. The reason is that this dimension is 12 meter. So total load will be transferred here, and that will go all the way to the foundations. And then we have cavity wall. The loading of cavity wall is 4 kilonewton per meter square. We just have cavity wall at the outer edges. The length of cavity wall is 2.5 plus 2.5 plus 0.75. So if you multiply 4 with the height of the wall, you will get the loading. So 4 times height of the wall, 2.5, 2.5, 0.75, we get this value. And again, foundation C will have cavity wall as well. So we are getting 23 kilonewton per meter. As foundation B does not have cavity wall, so that's why we don't have this portion is grayed out. Floor 2 is resting on foundation A and B. Floor 2 is this one, which is resting on foundation B and it is resting on foundation A. And floor loading is 1 plus 1.5, which means 2.5. The distance is 5.7 meters. So half of the loading will be transferred on foundation A, half of the loading will be transferred to foundation B. 2.5 times 5.7 divided by 2, same 2.5 times 5.7 divided by 2, we get loading from floor 2. On the other hand, floor 1 is resting on all 3 foundations. So foundation A will take half of 5.7 divided by 2, and foundation B will take half from here and half from here. It will have 5.7 divided by 2 plus 5.7 divided by 2, which means that you'll multiply it with 2 or you will get the whole dimension. And this is the reason we have for floor 1, 5.7 divided by 2 times 2.5 here for the middle one, because it was taking loading from both sides. So that's why we multiplied with 2. And then again for foundation C, because it's just taking loading from one side. So that's why 5.7 divided by 2. Then we have a brick wall. Brick wall is simply resting on foundation B. So brick wall has 2 kilonewton per meter square. We'll multiply it with the height. Height is 2.5 plus 0.75. So 2.5 plus 0.75 times the loading given, which is 2 kilonewton per meter square. We get loading of brick wall on foundation B. And then we have foundation itself. For foundation, we have the dimensions 0.3 times 0.6. And the loading is not given. So we are assuming that it is concrete foundation. This means that the density of concrete is 24 kilonewton per meter cube. We will multiply it with the area of the foundation. This will give us loading in kilonewton per meter. So let us see. 24 times 0.6 times 0.3, we get 4.32. Again, same is the case with foundation B, same is the case with foundation C. Then we'll add up all the forces. Foundation C is taking 45.85, B is taking 32.21, A is taking 52.98. It means that foundation A is taking more load. So that was all about today's lecture. If you have any questions, just put them in the comments. I will be able to respond to them.